Hi, I'm David. I'm one of the lecturers in the Maths Learning Centre at the University of Adelaide, and this is a rough and ready lecture about vectors. Okay, there's a lot that I could say about vectors, but I'm just going to say the main things about how vectors are related to geometry mainly. I will mention in passing some other bits and pieces, but I'm not going to go into detail on those. Just enough to be able to do the main things that you need to do in geometry with vectors. Okay, so when vectors were first invented, they were quantities with magnitude and direction, and that's a science definition of vectors. Okay, so vector quantity has magnitude and direction in science, which means it can be a certain size. They can be sort of bigger or stronger than others, and they go in different directions. So the classic is a force in physics, where you take an object and you can push on it with certain amount of effort in one direction or in another direction, or all these different directions that it can be pushed, and pushing it in different directions will produce, with the same force, will produce different results. So in that sense, the force, which is an idea in physics, is a vector quantity. And when Newton sort of first thought of this idea, he imagined them as arrows, where the length of the arrow represented the magnitude and the direction the arrow is pointing represented the direction. Like that. But the idea is, of course, that those arrows might actually not really exist, and the length might not be a real length. It might be, an amount of newtons. It could be like 20 newtons, or it could be like a, oh gosh, what else is a vector quantity? It could be momentum. What's momentum measured in? Oh, anyway. Can't remember a lot of my physics. But they could actually be distances. It could actually be like 4.6 centimeters as well. And the distance has a direction, and they call that a displacement. So that's the idea. The length of the arrow doesn't necessarily have to be a literal length. It's just representing a strength or a size of something. So that's science. And what Newton discovered was that there's all this cool stuff you can do of figuring out what's going to happen in a physics situation by using vectors. Okay, I'm not going to talk about that anymore. I mean, there's all this stuff about using trigonometry of non-right-angled triangles to figure some of these things out. And they talk about components and all sorts of things. But I'm going to talk purely geometrically from a mathematical point of view. So that's what happens over in science. In maths, vectors are normally used in a geometrical sense. And the maths that we do on them will translate back to applying to forces if you want them to, but we don't normally think about them that way. They're part of coordinate geometry. And over in maths, they are part of coordinate geometry, and then in other kinds of mathematics, we repurpose the word vector to mean anything that behaves mathematically the way that vectors behave in terms of things like addition and multiplication. And so we repurpose that word to mean other things as well. But in general, it's about coordinate geometry. And so I'm just going to have a quick interlude about points in coordinate geometry just for a minute or so, so that I can get a handle on what the vectors are doing. So, the idea of coordinate geometry is that every point, either in the plane or in 3D space everywhere, depending on what you're thinking about, can be given coordinates that tell you where it is. So you choose two axes. You choose an x-axis, which is usually horizontal, and a y-axis, which is usually vertical. And you locate every point on this by what it lines up with on the axes. So you mark distances along here, 1, 2, 3, 4, 5, and then backwards from where you declare 0 to be, it goes -1, -2, etc. And same for the y. And then if you just pick a random point like that, you can tell what its coordinates are by what it lines up with on the axes. It's 4 on the x-axis, so that one goes first. And then it's 2 on the y-axis, so that one goes second. And even better, like if you knew that it was 4, 2, then you could locate that point by lining it up with the appropriate points on the x and y axes. So this point here, for example, is 1 on the x-axis and -3 on the y-axis. And this point here is -2 on the x-axis and 0 on the y-axis. And this point here is 0, 0. And that's the idea of coordinate geometry. All right? I mean, that's the beginning of it. Coordinate geometry has a whole lot of other stuff involved with it. But we're going to start there. And you can do it in 3D as well, though it's harder to draw. So this is two-dimensional. In 3D, you might have an x and a y, and then there's a z-axis pointing upwards out of the page. And so you would have a point living in space. Just give me a moment. So for example, if you wanted it to line up with, so for example, this point just here, which lives in space, oh, it's very hard to see. This point just here, which lives in space, lines up with 4 on the x-axis and 3 on the y-axis and about 2 on the z-axis. And so it would have 3 coordinates. So you'd normally draw that on a diagram like this, where you imagine that x and y to be up this way and then falling down, and so it sort of falls backwards like that, and then the z-axis points upwards, and then you might have something like this point here, and this might be 3, 2, 3, for example. 3 for the x, 2 for the y, and 3 for the z. That's how you'd normally draw such a diagram. I feel like these all need some colours so that you can see where they are. Okay. Cool. All right. And there's no reason to do that sort of thing. I mean, you know, using numbers to locate points, it's not a bad idea. But we can get some cool stuff out of the coordinate geometry. We can get some cool stuff out of what these numbers are doing. We can you know, define lengths in terms of those numbers and angles and that sort of thing. And we can also create equations and say, okay, so this object, all of its points, when I sub in their coordinates, satisfy an equation, and so therefore they must be the equation for this object. And we can start to relate equations to geometry. And we spend a lot of time doing that over in calculus, where the equations are always y equals something. But there are lots of other equations which aren't y equals something, which we can also investigate. That's coordinate geometry, all the way back to Descartes. Well, I'm not entirely sure exactly when. In Europe in the, I don't know, something hundreds. Don't really know. I should look that up one day. So that's the idea. And where vectors come into that is that we can imagine them first as journeys between the points. Now I'm going to do all the rest of my examples from now on probably in 2D. So we imagine that vectors are journeys between points. Okay? Importantly, journeys that are the same length and the same direction are considered to be the same vector. Okay, so journeys between of the same length and the same direction are considered to be the same vector. So what does that mean? It's best to do it as an example. So let's see. So if I have the point 2, 3, and the point 1, 2, 3, 4, 5, 1. And it's traditional to give point 2, 3 and the point 5, 1. It's traditional to give points capital letter names so that later on I can just refer to it as the point P instead of the point 2, 3. The journey from P to Q, this journey here, which I will draw as an arrow with the arrowhead at Q. I don't put the arrow in the middle, I put it right at the end so that the person reading it can tell where the end of the vector is. So PQ, this is the notation, is the journey from P to Q, or if you like, the vector, because that's our new terminology. So it starts at P and it ends at Q. So what I meant was, when I said that, that journeys that are the same length and direction are the same, you'll see that this one goes across 1, 2, 3 and down 2. Okay? So anything that goes in that direction for that distance is the same vector. So I might, for example, say here at -2, -1, let us call that A. And if we go across 1, 2, 3, 1, 2, 3, and down 2, 1, 2 here at the point, we'll call it B, and this has coordinates 1, -3. It doesn't look like it's the same because I haven't drawn my axes with the same units, I'm sorry. This vector is the vector from A to B. A to B, and we say that PQ is the same as AB. They are actually equal. We declare them to be the same vector. So it doesn't matter where the vector is, it's the same vector. Okay. Cool. All right. Now I just want to point out that the vector BA is not the same as the vector AB because they point in different directions. Okay, so that's the beginning. That's what vectors are. We can give vectors their own coordinates based on describing how far they go in the x and how far they go in the y to get the entire journey. So these vectors are both equal to 3 minus 2 because they go forward 3 in the x and down 2 in the y. So we can have coordinates for vectors. So PQ is the same as AB, which is the same as 3 minus 2. So plus 3 in the x and minus 2 in the y. That's what we're thinking. Okay? You will notice that the coordinates I have written here for the vector look exactly the same sort of thing as the coordinates I have written here for the points. That's just the way it is. And the reason is going to hopefully become clear in a moment. Some people prefer to use square brackets for coordinates that are representing vectors and round brackets for coordinates that are representing points. Most mathematicians just don't care, and you will know from context which one it is today. And one of the reasons we do this is that there are times when it's useful to switch your perspective and consider a set of coordinates as a point or a vector depending on what you're trying to achieve with it today. Okay. So, I would like you to just notice something here, that this 3 is the same as 5 minus 2. That's how far it was between 5 and 2. That's how far the x changed. And this minus 2 is how far it is from 3 to 1. I mean, that's how I figured them out, right? I calculated really how far the x moved and how far the y moved, which you can do with subtraction. Subtraction is able to tell you with numbers how far apart they are, and not just how far apart they are, but which direction to go to get from one to the other. And we're going to reuse that idea of subtraction to start creating some mathematical calculations that we can do with points and vectors. And the first mathematical calculation that we can do is this. So the old location, the old place, plus the journey is the new place. Okay, this is the thing that we're going to be thinking. So we are going to say that point plus vector is a new point. So for example, I really should put a heading here. Vector calculation. Okay. So old place plus the journey is a new place. So for example, A plus the vector AB is B. And this is the fundamental idea of how we're going to create addition and subtraction and all those sorts of things with points and vectors. So if you have a point and you add the vector AB, you will end up, your answer will be the vector B, because this is the journey that goes from A to B. So if you start it here and then do this journey, you will produce that. So we're going to see this as addition because that's how it worked with numbers. When you first learned to do addition, well, not maybe when you first learned, but a little later on, you learn to say maybe 18 plus 3, and you go, all right, 18, 19, 20, 21. Okay, so 18 was a place to start counting, the 3 was how many to count, and the 21 was the answer. And so that second number was different in what it was doing than the first number, and we're being really clear on that here because this is a vector and this is a point. So we've already been doing vector point plus vector addition way back when you were small, when you were counting on. Okay, and what this also means is that a journey is the new place minus the old place. Okay, if that's what subtraction means, it's the opposite of addition, then we can do that. Okay, so we've got some vector our first vector calculation. So let me just do an example. If P is the point 1, 7, and Q is the point 3, 3, 5, maybe not 3, 5. We're going to do a half 9. Okay, so I just want to point out here there's nothing that says that vectors have to have whole numbers in them. It's perfectly okay to have fractions or even square roots or anything else in them. So any numbers are okay in that spot because we can have numbers between these things on the axes here. Okay, so there's an example. If P is 1, 7 and Q is a half 9, find PQ and QP. Okay, so as far as we're aware, PQ is the end minus the beginning. Okay, that makes sense. P plus PQ is Q, and so PQ must be Q minus P. And so I'm just thinking in my head, end minus beginning. Just so you know what I'm thinking, I'm not writing it down. And Q is a half 9, and P is 1, 7. And when you subtract these, we already know that we did it on our diagram. You just have to subtract the x's and subtract the y's, and that will do it. So a half minus, I'm just going to explicitly write it, a half minus 1 and 9 minus 7. The comma there is separating these two. I need the brackets on the outside, or it's not a point, it's just a list of numbers. Or in this case, not a point, a vector. And a half minus 1 is negative a half, and 9 minus 7 is 2. So that's what PQ is. And QP is going to be P minus Q, because the end here is P and the beginning is Q. And so that's going to be 1, 7 minus a half 9. And I can do all that in one go without doing this calculation this time. 1 minus a half is a half, and 7 minus 9 is minus 2. And you will notice that the coordinates of PQ are the minus of the coordinates of QP. And that's always true. And so we can have this new operation of minus a vector, the negative of the vector. It's not like there's such a thing as positive vectors and negative vectors, because like this one's got a negative coordinate and a positive coordinate, and this one's got the other way around. So it's not like the vector as a whole is positive or negative, but the action of doing the negative is a thing that I can do. Okay. So now it's going to become useful to have, I might summarize these in a little bit and put them all on one page, but it's going to become useful to give names to my vectors that aren't talking about which points they go between, because at the moment, sure, PQ is the same as AB, but they're referring to the points A and B. If I had a new name for just what that vector was, I'd be able to do some stuff. So I'm going to have to do that. But first thing that we've noticed is that minus PQ is the same as QP. Well, probably better to say that QP is the same as minus PQ. That's one of the rules that we have so far. And also, we also know that what that means is that the minus, the negative of a vector is the same vector but in the opposite direction. So QP, PQ goes from P to Q, and if you minus it, it goes from Q to P. So we could say that minus V, so it's traditional for vectors to be, the name of a vector to be a small letter. So big letters would be points, small letters are something else, a small letter. And in a textbook it would be written in bold, but I can't do bold on paper. It'll look messy, and so I'll do underline. Though some other people put an arrow on the top of it, or a squiggly line, I'll just do underline. Minus V is the same as V, but in the opposite direction. Okay, so already we're starting to build up some things that we can do with vectors. We can add points and vectors, and we can subtract points to get vectors, and we can minus vectors. And that's interesting. If we can minus them, we must be able to do some other stuff too. So the next thing we're going to do is scalar multiplication. So we can make vectors longer or shorter by multiplying them by something. Okay, so since in the same way that minus V is the same as V but in the opposite direction, well, something like K times... Well, let me just draw a picture. What if this was a vector? I know it doesn't have an arrow. Well, actually, just a second. What if this was a vector? What if this was a vector? I'll just... It's an arrowhead. So if I want it to be the same direction but twice as long, then it would be reasonable to say that this vector was 2 times the original vector. And if I wanted to have my original vector back and I wanted it to be half as long, it would be reasonable to say that this vector was half of the original vector. Probably shouldn't put that one through the photocopier later, so I'll just chuck that piece of paper out. Don't really want Play-Doh in my photocopier. So, K times V, where K is a number, for K a number and V a vector, is the same direction as V, but K times the length. Okay, this is called scalar multiplication. And the word scalar literally means thing that scales. When you scale something, you stretch it or shrink it. And so we are multiplying by a number, and that number is being thought of as a thing that scales the vector. So that's what scalar multiplication is. And just as an example, 2v, well, it's not necessarily in the same direction. It's only in the same direction if k is positive. It's in the opposite direction if k is negative. Opposite direction if k is negative. Okay. So, for example, 2v is twice as long twice the length of v, and half of v is half the length of v. That's the idea. Okay, I'm just going to draw a quick picture of that. So if this is v, then 2v would be twice as long. 1, 2. That's 2v. And if this was v, then half of v would be half as long. Okay. Let me do another example, because we can use this idea to start calculating some cool stuff. So this is just an example of the idea. This is an example of doing an actual calculation. So if C is 1, 7, no, I already used 1, 7. Let's stick a negative number in there. Minus 2, 8. And well, it's traditional to use two letters that are next to each other, but I choose a different letter entirely. C and K. And K is 0, 5. I know I can use not whole numbers, but I just don't feel like it right now. Find the midpoint of the line segment CK. So here's an important thing about why we have arrows on the top of vectors when we're giving them as names, as journeys between 2 points. Just writing CK without an arrow means it's just the line segment, and that's like a length, and it goes in either direction, and that's fine. The arrow carefully distinguishes just a line from a vector. Okay. So I'm just going to draw a diagram of this. So here's minus 2, and here's 8. There's the point C. And 0, 5, 0 for x and 5 for y. About there. There's K. And this is the line CK. And the midpoint would be, well, halfway up that line, or down that line, depending on which direction you come from. Okay, well, let's just think about this. The vector CK, we can figure that out. So CK would be K minus C, n minus beginning, which would be 0, 5 minus 2, 8. So 0 minus negative 2 is plus 2. And 5 minus 8 is minus 3. That makes sense. It went, there's 5 on the axis. It went forward 2 and down 3. Beautiful. But we don't want to go all the way from C to K. We only want to go halfway. And so we can say that half of CK is a half of 2 minus 3. Now, here's how to do the calculation. You just halve those numbers. Okay, I didn't actually show how to do it earlier, I'm sorry, but here's my example of how to do it. Halve those numbers, so half of 2 is 1, and half of minus 3 is minus 3 over 2, so minus 1.5. And therefore the midpoint of CK, well, it must be C plus half of CK. The idea being that if I want to do half the journey, well, I just add half the journey. If CK is the journey from C to K, and I only want to go halfway, well, I'll add on half the journey. And so that will be C, which was minus 2, 8, plus 1 minus 3 on 2. Well, if I move that back just a little, I'll be able to fit the whole thing in on the one page. Minus 2, 8. Plus 1 minus 3 on 2. So minus 2 plus 1 is negative 1. 8 minus 3 on 2 is 8 minus 1.5, which would be 8 minus 1 would be 7 minus a half, which would be 6.5, which would be 13 over 2. Let me do that another way. 8 would be 16 over 2. 16 minus 3 over 2 is 13 over 2. And so there's the midpoint there. And I know that that's a point because I said it was a midpoint as opposed to a direction. So we can start using scalar multiplication as a way of finding the locations of interesting points. Okay, and through that example I've showed you how to do scalar multiplication. I probably should have done that earlier. But really, if you multiply by a number, then you multiply both of the coordinates by that number. Okay. So what have we got so far? We can add a vector to a point and get a new vector. We can subtract 2 points to get the journey between them. We can minus a vector to get one that's in the opposite direction, and we can multiply by something to get it both simultaneously in the opposite direction if it's negative, or to stretch or shrink the length. Okay. And there's nothing stopping us multiplying it by things other than 2.5. We can multiply it by 3, we can multiply it by 1.5, we can multiply it by root 7. Any of those is fine. So, okay, these are all things we can do. Interestingly, I've talked about the length of a vector, but I haven't told you how to find that yet. So, it's probably time to do that. Of a vector is found using Pythagoras' theorem. If you're in the USA, you probably call it the Pythagorean theorem, because, you know, technically we don't actually know if it was proved by Pythagoras at all. It might have just been one of his students or his, you know, devout religious followers. Okay, and it's easiest to do as an example, but I'm just going to actually write down the formula. You know, if V is, say, AB, then the length of V. So some people do this as a double, double strike like that, and some people do it as a single. It doesn't really matter, but I would just check if you learn maths, further maths or in any other places, that you check that you're using the right notation. And so this is the square root of a squared plus b squared. And it works like this. If this is what v is, and that distance is a, and that distance is b, because that's what the AB refers to, then by Pythagoras' theorem, the length of v squared would have to be a squared plus b squared. This is the idea. Okay. So if I want a vector that's half as long, I multiply by a half, and that should produce a vector with literally half the length. So let's give it a go. I just want to prove it. E.g., let's do it as a little proof. Prove that in 2D, half of V, the length of half of V is half of the length of V. As it should be, right? It's the same vector, but it's half as long. Now, I've told you what it is. It's the same vector, but it's half as long. But I really want to, I'm just going to say using, you know, by calculating distances, okay, by calculating lengths. So I would say let V be equal to AB for some A and B. You have to always tell people what your letters stand for. And then half of V would be half of A times, and half of B. Okay. So the length of V would be the square root of A squared plus B squared. All right. And the length of a half of V would be the square root of a half of A squared plus a half of B all squared, because we take the coordinates of half of V and we put them in there. And we're supposed to calculate on this until it comes out to be half of V. Well, let's see. A half squared is a quarter. I'm actually just going to leave it as a half squared. Okay, squaring can be brought across multiplication. There's a half squared in both of those. Now, square rooting can be brought across multiplication as well. So this would be the square root of a half squared, which is a half, which is a half of the length of V. Cool. So this is a little proof based on calculating lengths. And so just to show you how I went about it, my goal was to show that this was equal to that. And I decided that the quickest way would be to calculate what the length of half of V was and hope to notice that I could find the length of V in it. So I found the length of V so that I could look for it. Then I found the length of half of V and I calculated on it until I got to the point I was looking for. And you'll notice that it's just equals, 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 equals. And equals like this is a floating one like this says that this is supposed to be equal to the line above. I don't have to repeat this because it's just saying it is equal to which is equal to this, which is equal to this, which is equal to this, which is equal to this. I mean, and to finish it off, I should probably say, you know, therefore, the length of half of V is half of the length of V. And that would work no matter what K is, unless K was negative, in which case this square root here, when I did the square root of minus 2 squared, I do not get minus 2. So I'm just going to put a note here. Note. The length of like minus 2V is actually just 2 times the length of V. Not minus 2. Because the length can't be negative. So it wipes out negatives. Okay. Cool. So that's lengths, and they really are working the way we want them to. And this is a really cool thing. Now we can find the lengths of the sides of, say, triangles that are made out of points with coordinates by literally finding the vector between them and then finding the length of the vector. And I should put a note here that in 3D, lengths are like this. In 3D, if V is equal to, and it has 3 coordinates, then the length of V is the square root of A squared plus B squared plus C squared. So you just whack another plus something squared under there and it'll work out to the right answer. Okay, and in 4 dimensions, it'll be A squared plus B squared plus C squared plus D squared. What does it mean for a vector to be in 4 dimensions? Well, that's a whole other story, and I'm not going to discuss that today. But what we normally do is just say, well, it's probably going to work roughly the same as how the geometry works in 2D. We'll just do it on the numbers, and it should work out fine. Okay. So what have we done so far? We've done journeys, we've got minuses, we've got scalar multiplication, we've got lengths. That's pretty cool. All right. Cool. I guess there's one thing to mention here that I'm having trouble figuring out where to put it, and I'm just going to put it here while we're talking about lengths. If the length of a vector comes out to be 1, we call it a unit vector. So if the length of v is 1, then v is called a unit vector. That's so important, I'm going to box around it. Then v is called a unit vector. So unit vectors are important because using we've got some unit vectors already that you've seen. The journey between any 2 points that are marked on this axis is a unit vector because they're length 1. And that's useful to know. And those unit vectors along those axes help us to mark out positions on that axis. So if I wanted to draw a new x and y axis in a whole different direction, because I thought it would be easier to look at it sideways, I could use a unit vector pointing in a different direction in order to do that. And so it's actually a very useful thing to be able to do to find unit vectors. And what you normally do to find a unit vector is figure out a vector in the direction that you want it to be, and then multiply it by the right thing to make the length 1. So I'm just going to do that now. If m is the point 1, 11, 8, and n is the point -1, 6. Actually, do you know what? Give me a second. So I'm going to go -1 and 17. Find a unit vector in the direction of mn. Okay. So if I want a vector that's in the same direction as mn, I could first find mn, and then if I multiplied it by any number, it would still be in the same direction, as long as that number was a positive number. If I multiply it by a negative number, it would be pointing in the opposite direction. And so I would like, and if I pick the right number, I should be able to make the length whatever I want. Because I know that if I have mn, and I multiply it by 2, it'll be twice as long. And if I multiply it by 3, it'll be 3 times as long. And if I multiply it by a half, it'll be half as long. And if I multiply it by a third, it'll be a third as long. So if I can multiply it by the right fraction, I should be able to make it the length 1. Okay, so let's see. Mn is n minus m, which is -1, 17, -11, 8. So -1 minus 11 is -12. 17 minus 8 is 9. Okay. And so if I found how long this was, then I could do the right fraction to get that length to be 1. Okay. I see these both have a 3 in them, so I might just take that out. This is the same as 3 lots of -4, 3. And so I don't really need to know how long mn is, because this vector points in the same direction as mn as well. And so I could use that vector instead. That'll be a little easier. So let's see. The length of -4, 3 is the square root of -4 squared plus 3 squared. That -4 is inside the square, very important, because that gets squared, because we're really doing a literal length. So that's going to be 16 plus 9, which is 25, which is 5. Okay. So the length of this vector is 5. So I want a vector whose length is 1. So if I multiply this vector by a fifth, the length should multiply by a fifth, and so the length should be 1. So let's see. the length of 1/5 of minus 4, 3 should be 1. So therefore, 1/5 of minus 4, 3, which is minus 4/5, 3/5, is a vector, a unit vector in the direction of Mn. Okay. And that's pretty much it. So if you want a unit vector in the opposite direction, it would be 4/5 minus 3/5. Now this one came out as neat little fractions because I deliberately chose it so that my square root came out to a whole number. But it doesn't always work out that way. It often works out to have a square root in it. In the direction of AB. Let's do it as BA, just to mix it up. Okay. So let's see. BA is A minus B, because it's end minus beginning, which is 10, 3 minus 1, 2, which is 9, 1. Let's just check that. To get from B to A, I have to add 9 and take 1. Add 9 and add 1. Yep, that'll do it. Okay. So the length of BA is the square root of 9 squared plus 1 squared, which is the square root of 82, which isn't going to do anything good. I mean, 82... it's a multiple of 2. I can't think of any numbers that I could pull out of that. All right. And so therefore, 1 over root 82 of BA is a unit vector, because it was originally this length, and if I multiply by root 82th, then that should make the length equal to 1. And so that's is a unit vector in the direction of BA. Now I should just say something. If you look carefully at what I've done, this equals in the middle of this sentence is 1 over root 82 of BA is equal to, which is equal to 9 over root 82, 1 over root 82 is a unit vector in the direction of BA. If I said is equal to and then is, it wouldn't make any sense. So this is read aloud as a which is equal to. And that's pretty much it. There's nothing much more to it than that. I should say as well that some people say the phrase a unit vector of BA. That's not correct. The unit vector there lives all by itself. It existed before BA was there. It just so happens that I found it from BA. It doesn't belong to BA, it just happens to be in the same direction as BA. So the correct thing to say is a unit vector in the direction of BA. Okay. All right, so we've defined what length is, and we've got a special length, which is 1, and that was useful. I guess the last thing to do is, well, if we can minus them like this, then I think it should be possible to add 2 vectors without there being a point nearby. So addition. So let's see. Well, you could imagine that I guess adding 2 vectors would be doing one journey one after the other. And you could imagine starting at a point and doing a vector and then doing another vector and getting to wherever the point goes. So I'm just going to just set this up. If we had the point P and then we did PQ and then we did QR, that should be R, right? So if this is P, and this is Q, and this is R, then that's PQ and that's QR. Okay, so the P plus PQ is Q, and the Q plus QR is R. All right? So let's just do this thing. P plus PQ plus QR should be R, and that's because P plus PQ is Q. And Q plus QR should be R. Okay? So we notice this. And we also notice that P plus PR is also R. So there's PQ, there's QR, and there's PR. So P plus this thing is R, and P plus this thing is also R. So I would therefore say that PQ plus QR has to be PR. And so now I have created a way of adding vectors. If I want to add vectors, I put them nose to tail and figure out the journey that goes direct from one to the other. So geometrically, to add vector u plus vector v, arrange u and v head to tail, and u plus v is the journey from the beginning of u to the end of v. It doesn't really matter what direction they're going. Like that. I'm just going to colour them in different colours. So there's u, there's v, and there's u plus v. So that's what you do geometrically, but ultimately we can just add them together the way that we added and the way that we subtracted points. We're just going to add and subtract their coordinates. So that's geometrically. With calculation, add the coordinates. So that's how addition works. There you go. And remember, we can move vectors to be wherever we want to put them head to tail, because remember, any journey is the same, as long as it's the same distance in the same direction. It doesn't really matter what points it's between. It'll always produce the same answers. So I think that's everything that we could possibly do to vectors. Let's just sum that up. And see what we've got so far. So far, so sum up what we have so far. We have that P plus PQ is Q, and PQ is Q minus P. Okay. And we have that PQ plus QR is PR. That's some stuff we had before. So there's some things about how vectors relate to points. Okay. And then we also had some operations we can do on vectors. We can do scalar multiplication. So we had kv, which we did by multiplying the coordinates by k. And what that did is it multiplied the length by k. But kept the direction. Okay. That was scalar multiplication, wasn't it? And we had addition. U plus v, we add coordinates. And what we did is that we put head to tail and found the new journey. Okay. And is that everything we did? Oh, we had the length. The length of v, use Pythagoras. Okay. So if we can do, okay, so that's pretty good. There are two more operations that we can do, which relate to angles, and I'm going to get to that in a second. But before I do that, look, if you can do an operation on things, then you need to know how those operations interact with each other. We've already got one. We know that if we multiply v by a scalar, then it multiplies the length by that scalar. And so we should just write down some rules. So some rules. K times m times v. If you multiply the numbers together first and then multiply by v, it's the same as multiplying by k. Doesn't matter what order you do them in. You can multiply v by m first and then by k, or you can multiply the k and m together and then multiply by v. It's the same answer. We know that k times the length of v we know that the length of kv is the same as k times the length of v if k is positive. And minus k, the length of minus kv is also kv if k is positive. Okay, because anything that's negative, the negative goes away. So that's how scalar multiplication interacts with itself, and it's how it interacts with length. And I guess we could do addition. Well, if you multiply them by a scalar after you've added them, it's the same as if you multiply them by a scalar before you've added them. So that's sort of like a distributive law. Cool. And how does addition interact with length? Not very well at all. Not helpful. There is actually a rule that you know that the length of u plus v is actually shorter than the length of u plus the length of v, but I'm not going to go with that. You don't really need to know that today. And I guess how does addition interact with itself? Well, it's exactly the same as addition for ordinary numbers. You can do it in whatever order you want. U plus v is the same as v plus u. And minusing is the same as multiplying by minus 1. So I'm just going to pop that in there. Minus v is the same as minus 1 of v. And why, David, you're saying, why is that such a thing? It's like, well, just a second, minus v was the vector that was in the opposite direction, and no one said that it had to be the same as what you got when you multiplied by minus 1, but it is, because the length doesn't change and it's in the opposite direction. Okay, so there's some rules which are important to know. And that means that we can basically do algebra the way that we expect to do algebra with these vectors. And just for your information, when mathematicians later on extend the meaning of vector, that's what they do. They go, well, anything that follows these sorts of operations that we're used to doing on vectors, we're going to call vectors. And so they start to say things like functions are vectors and matrices are vectors and all sorts of fun stuff like that. Okay, so that's what we've got so far. Now what? Oh, I said there were two more operations that I could do. And really one of them exists because of the other. Well, no, one of them exists because of the whole sort of all sorts of other esoteric stuff and the story of Hamilton and Lewis Carroll, and it's very complicated. Magnetism, and there's physicists, and it's all very complicated. But today we're going to pretend that it comes about from angles. So the last thing that we're going to do is angles. Okay. So, we've talked about the lengths of things, and I talked about how, so if I had a triangle with its coordinates marked, I could figure out the lengths of those triangles. Now I want to figure out the angles in the triangle. And sure, I could use the lengths, and I could use like the cosine rule or something, and I could calculate the lengths of the triangle, and that'd be great, but we're going to do a very fancy trick, which is called a dot product. And it's going to help us find the angle. So here we go. The dot product of two vectors. So let's see. If u is equal to like AB and v is equal to like CD, then u dot v is you multiply the matching coordinates, a times c, and you multiply these matching coordinates, b times d, and you add them together. So very important to notice that the first two coordinates end up together, and the second two coordinates end up together. A very common mistake that people make is to multiply the first vector and multiply the second vector, but it's actually across the two. And that seems like a weird-ass thing to calculate. You'll notice that it starts with vectors. Sorry. You'll notice that vector dot vector is a number, or scalar if you like. That's important. You'll also notice that I've very carefully drawn a great big dot. That's important too, because there are other ways to multiply vectors together, and it's called a cross product. So you are not allowed to use a cross like you did with multiplication back when you first learned multiplication in primary school, and you are not allowed to just put nothing there because the nothing there doesn't specify what kind of multiplication there is. There is more than one kind of multiplication for vectors. I'm only telling you about the dot product, but there is another one called the cross product, and they're different. So you must put the dot in. Okay. Seems like a weird thing to do, but it turns out that it is wonderfully helpful for figuring out the angles between things. Okay? All right. Angle. Okay, so just wait a second. Just let me note what it looks like in 3D. Note. In 3D, if u is equal to a, b, c, and v is equal to d, e, f, that's not the number e, it's just a letter, then u dot v is a, d, b, e, and c, f. You still multiply the matching coordinates. And you add them up, but there's just 3 coordinates this time. Also note, if you know anything about matrices, then u dot v is the same answer you get if you put a row matrix A, B and a column matrix C, D, like that. Which is why it's not all that unusual a thing to want to do. Dot products help relate vectors to matrices, which is a really useful thing to be able to do. Okay, so they're just some side notes. That's what the dot product is. If you want to calculate an angle, you can use the dot product, and it's really cool. I think. It's a bit of a magic trick. I'm not actually 100% sure of why it works. I'm sure I could do some trigonometry and make it happen. Okay, just a second. I'm going to need to give a name to the angle between it. So if theta is the angle between vectors u and v, then cosine of theta is u dot v divided by the 2 lengths. There is no multiplication sign here because these are numbers. And in fact, dividing by the lengths really isn't a thing. We never said we could divide by length, so technically it's more that that u dot v is the same answer as the length of u times the length of v times the cosine of the angle between them. Okay, so what this is saying is that the dot product of u and v is related to both of their lengths. So the longer the vectors are, the bigger the dot product's going to be. And that's useful. I mean, if you multiply, when we multiplied them by scalars, it changed their lengths. And so when we do this new multiplication of 2 vectors, it should be related to their lengths. But it's also related to the angle between them. If the angle between them is wider, then the dot product will tend to be bigger. No, that's wrong. If the angle between them is sort of close, is smaller, then the dot product is going to be bigger because cos theta is bigger when the angle is smaller. Okay? And if that angle is 90 degrees, cos of 90 degrees is 0, and so the dot product's actually going to be 0. So it's sort of, if they're sort of pointing in the same-ish direction, the dot product will be higher than it will be if they're pointing at right angles to each other. And that's going to be really useful in a moment. Okay, some people write, so cos theta is is 1 over the lengths of both of them times u dot v, if you like. All right. Cool. So this is how angles are related to the dot product. And this is really sweet, and it's particularly nice in 3D because it works in 3D as well. This angle is always going to be between 0 and 180 degrees. Because that's what your calculator will produce when you do cos inverse of something. And also, you don't really care about the angle all the way around the other side. It's sort of like the shortest angle between the 2 vectors. Okay. And that's everything. The only other thing that you would want to know is how the dot product interacts with plus and minus and times and stuff. And so we can do this. So just some rules. If you have k times u times v, dot v, then you can do the dot product first and then times k. That'll work. And that works even if k is negative. And u dot v plus w is the same as u dot v plus u dot w. So it's a bit like you expand out the brackets, expand out the multiplication like you did before. When you did ordinary multiplication, that works as well. And it doesn't really make sense to talk about u dot v interacting with the length because u dot v is a number and you don't have a length. So we're not going to talk about that. Okay, and this works even if the k is negative. So there's some rules. And that's pretty much everything we have on how to do stuff with vectors. Let me just do an example of finding the angle between two vectors so you can see how it works. Find the angle between u, which is going to be 1. I always start with a 1. Why do I do 1? Let's do 4 minus 3. And v is going to be, I don't know, a half 2. Okay? Okay, so let's see. Now, I haven't been given a name for this angle, so I'm going to give it a name. I could call it theta or alpha or anything I want, but I might as well call it theta. Be the angle between u and v. Then cos theta is 1 over the length of u, the length of v, times u dot. Actually, you know what? You can divide. Ha! U dot v isn't a vector. It's a number. So we totally can do this division. Sorry about that. Great. There is such a thing as division for numbers. Okay, so I'm going to need to find what u dot v is, what length of u is, and what the length of v is. So u dot v is 4 minus 3 dot with a half 2. So the x's will be 4 times a half minus 3 times 2, which is 2 minus 6, which is negative 4. The length of u is the square root of 4 squared plus minus 3 squared, which is the square root of 25, which is 5. Nice. The length of v is the square root of a half squared plus 2 squared, which is the square root of a quarter plus 5. So that's like root 5 divided by 2, because I can do those two roots separately. Okay. And so therefore cos theta is u dot v, which was negative 4, divided by 5 times root 5 over 2, which is minus 8 over 5 root 5. All right, well, so theta is going to be cos inverse of minus 8 over 5 root 5. Now, very important, you cannot say cos inverse equals. Cos inverse is the name of a function. It's the opposite function of cos. So the idea is that when we do cos on this angle, it comes out to this answer, which means when we do cos inverse on this angle, answer, it should come out to the angle. Okay, so I get my calculator and I type that in. My calculator's in degrees, just there. I could change it by pressing this button here, but I've got it back to degrees. And cos inverse, there's cos inverse is in orange there, so cos inverse of minus, that's probably not going to like that minus, is it? Minus 8 divided by 5 times square root of 5, which is 135.7 degrees, approximately. Oh, actually, do you know what? Approximately. Now, what you don't want to do is figure out what this is and then do it afterwards. So let me just show you something. Minus 8 divided by 5 times square root of 5 is minus 0.715. So that rounds off to minus 0.72. Watch what happens when I do cos inverse of minus 0.72. I get 136.05. It's actually out by like 0.6 of a degree-ish. And it will be wronger in some places than others. And so don't round off first and redo it. Keep the answer, just do it all at once. Alternatively, I could have done minus 8 divided by 5 times square root of 5, and then done cos inverse of the answer, and that would have been fine as well. I just want to check if I believe this. The negative number here, the negative dot product will always come out to an angle that's above 90 degrees. And I just want to draw a quick picture of these vectors. So 4, 3, 1, 2, 3, 4, negative 3, 1, 2, 3, that's U. For negative 3, and V was a half 2, half 1, 2, like that. Half 1, 2, so it's about there. Oh yeah, it's about, you know, it's past the 90 degree point, which would be there. Okay, doing well. Okay, I believe it. Just let me do one more example of finding angles. What if I had specific points? Two minus 5 and r equals, I don't know, 3, 0. Let's do that. Find the angle PQR. Okay, so this is a pure geometry question, but we can do it with vectors. I'm just going to draw the picture. 1, 2, 3, 4, 5, 6, 7, 8. So there's 1, 8. 2 minus 5. Oh, wow. 1, 2, 3, 4, 5. It's at 5. It's about there. And r is 3, 0. That's there. A ruler wouldn't be the worst thing. So that's the angle I want there. I shall give that angle a name. So let's call it alpha today. The angle PQR. Okay. So that angle is the angle between the vector QP and QR, because I can draw them there. So alpha QP and QR. It's important that the point that the angle is being calculated at is the beginning of both of these vectors. Otherwise, it's not going to work out to the right answer. So it has to be Q to one and Q to the other if Q is the point that's actually on the angle that you're drawing. Okay, so let's actually calculate all of these things. We're going to need dot products and lengths. So QP is P minus Q, which is 1, 8, minus 2, negative 5, which is negative 1. No. Yep, that's right. Negative 1, minus 5 would be plus 5, 13. So that makes sense. Minus 1 up 13, that gets from Q to P. And QR is R minus Q, which is 3, 0, minus 2, minus 5, which is 3 minus 2, which is 1. 0 minus 5 is plus 5. Beautiful. So I'm going to need the dot product of these and their lengths. So QP dot QR is minus 113.15. So I'll get minus 1 times 1, which is minus 1, plus 13 times 5. Wow, 13 times 4 is 52, 65. 64. So it's positive, which means the angle's less than 90 degrees, and it looks like it, so that's good. The length of QP is the square root of minus 1 squared plus 13 squared, which is the square root of 170. The length of QR is square root of 1 squared plus 5 squared, which is the square root of 26. And so therefore, cos of the angle is QP QR dot QR over the length of QP, the length of QR, and QP is dot QR is 64, and this is root 170, and this is root 26, and so alpha is cos inverse of this. So let's see, cos inverse of what was it? 64 divided by square root of 170 times square root of 26, which is 15.7 degrees, approximately. Okay, that looks pretty small. Yeah, it looks like about 15 degrees, so we're doing well. All right, cool. Now, so we can calculate angles, we can calculate lengths, we can find unit vectors, we can add and subtract vectors. Okay, oh, I've forgotten something. I just said something back here and I'm going to need to just repeat it again. You know when I did scalar multiplication, that kv is in the same direction as v, but k times the length? Okay. Well, that's saying that if I multiply by a scalar, I get something that's in the same direction or the opposite direction. Alternatively, if it's in the same direction, it must be possible to multiply it by a scalar and to get it. So if two vectors are in the same direction or opposite directions, there must be a scalar that you can multiply one by to get the other. And I didn't mention that at the time, but I really want to mention it now because I forgot about it and it was important to say. So in this one, we used that fact. We went, well, if it's halfway, it must be half of what it was before. These two vectors are in the same direction. So we managed to actually create those there. And over here, when we did the unit vector, we went, well, we want a unit vector in the same direction, and we went, it must be possible to multiply mn by something to get the vector we want. So we've already used the fact I'm about to write down, but I just forgot to write it down at the time. So, sorry about that, but I'm going to put this in parallel and perpendicular. Look, I'm going to do them separately. I don't want them together. We're going to get confused. So, parallel. Two vectors are called parallel if they point in the same or opposite direction. they're same or opposite. And that's the definition. And the important thing about parallel vectors is that if one vector is a scalar multiple of the other, then they're parallel. And if they're parallel, one of them will be a scalar multiple of the other. In fact, both of them will be a scalar multiple of the other, but just be a different multiple. So it's like a theorem. Two vectors are parallel when one is a scalar multiple of the other. And what that means is it's possible to find vectors that are parallel to each other using that rule. So let me give you an example of finding a vector that's parallel to another using one extra piece of information. Let V be minus 6.5. Okay. And W is 2m for some m. Find all values of m for which W and V are parallel. Okay, that's a classic sort of question that maths teachers tend to put in exams and assignments. And let's figure it out. So if they're parallel, one of them must be a scalar multiple of the other. So we must be able to say V must be k times W for some k. That must be true. Okay? So I can start there. And V was minus 6.5. And K was 2m. Yep. And that's the same as 2k km if I multiply these both by k, because that's how it works. Now, two vectors are equal if they're the same journey. So that must mean that minus 6 is the same as 2k and a half is the same as km. So therefore, minus 6 is 2k, and also a half is km. Now, if minus 6 is 2k, I can divide both parts by 2, and I'll get minus 3 equals k. I'm just going to call this 1 and this 2, and I'm going to substitute into equation 2, and so we have a half is km, and a half is therefore minus 3m, and so if I divide by the minus 3, I'll get minus a sixth equals m. And so therefore, m is minus a sixth, and w is actually 2 minus a sixth. Now, I believe it is a coincidence that v is minus a 6.5 and w is a half minus a sixth. That is total coincidence. That you do not always get parallel vectors having the same numbers switched around. That's my fault for picking this to be a 2, which is 1 over that. And it's to do with the number 6 as well, and how it's related to the number 2. So don't always do that. It doesn't always work. You can't just switch the numbers around like that. Okay, so that's just an example of how you might be given some information by a teacher and being asked to use the fact that it's parallel to figure something out. Okay. Perpendicular, that's parallel. Parallel means pointing in the same direction or in opposite directions. I believe para means similar to or next to. So like a paramedic is next to the medics. A parable is a story that's sort of next to the real story. It's about other people, but it's telling you a story about something else. So parallel means next to, and so it's next to, and lel is about lines. Lines that are next to each other. Okay, so now let's talk about perpendicular. There's another word that you might see in terms of vectors, which is orthogonal. And they both mean at right angles. If they're at right angles. I don't actually know the background of the word perpendicular, I'm sorry, but I do know the word orthogonal. Ortho means correct and gon means angle, and so a correct angle is a right angle. That's what the right in right angle means. It's the right in terms of correct as opposed to the right in terms of left and right. Okay, so, and you can tell if they're perpendicular directly from the dot product. So if you want your angle to come out in this formula, if you want your angle in this formula to come out to 90 degrees, cos of 90 degrees is 0. So you're going to need this to be 0. And the only way this is going to be 0 is if that's 0. So if the dot product is 0, they're going to be perpendicular. So two vectors are perpendicular if their dot product is 0. That is the condition that you can use to tell if vectors are perpendicular or not. And in fact, mathematicians, when they create some fancy mathematical systems where they have some things that they call vectors, but they aren't vectors in the traditional sense, when mathematicians come up with these crazy systems where there's vectors that aren't really vectors, in some of them it's not possible to really talk about what an angle is, but it's totally possible to talk about dot product. And so we can talk about things being orthogonal when their dot product is 0, even if there's no such thing as an angle, which is kind of fun, really. Okay, so what that means is if I asked the same question as I had before, but instead of asking what does m have to be to make them parallel, but what does m have to be to make them perpendicular, then I can solve that problem too. So I'm actually going to repeat the same question. Let v be minus 6.5 and w be 2m for some m. Find all values of m for which w and v are perpendicular. Okay. So, let's see. Perpendicular means at right angles, and perpendicular means that the dot product will be 0. So if w and v are perpendicular, then w dot v is 0. Which means that wrong way around. It doesn't matter, the dot product comes out the same either way. 2m m dot minus 6, a half should be 0. So 2 times minus 6 is minus 12. M times a half is a half of m. So a half of m should be 12. So m would have to be 24. So therefore, to be perpendicular, m is 24, and w works out to be 224. Okay, well, let's just check that. 224 dot minus 6 a half. 2 times minus 6 is 12. Half of minus 12, half times 24 is 12, and so yes, they do come out to 0. Okay. Whew. Well, that's a lot of stuff going on with these vectors. We can add them, we can multiply them by scalars, we can dot product them together, which allows us to find angles and to tell when we're perpendicular, and the multiplying by scalars told us when they were parallel, which is kind of cool. We have the scalar multiplication, which is about parallelism, and we have dot products, which is about perpendicularity. And I think that's kind of cool that they relate to each other that way. The only thing I would do at the end here is to have some sort of example that described, sort of put all this together and sort of made it a bit tricksy. So I'll just look some of those up. Okay, I've thought of one. I'm just going to start on a whole new page. Let's see. Okay. P is equal to 2, 3. Find all points. No, we're not going to do that. And Q be equal to, what are we going to do? Let's say 5, 10. Okay. Find all unit vectors which make an angle of 30 degrees with PQ. Now, it's a random question with random things just being connected in random ways. It's not particularly meaningful, but you need to be able to do these sorts of things because people keep asking you. So I'm going to draw a picture of this first to get a handle on what's going on. So there's an x-coordinate, there's a y-coordinate. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to have to fit that in to get my Q. So I'm just going to make that a little longer. 1, 2, 3, 4, 5. Okay, so probably don't need all of that space. So 2, 3, 1, 2, 1, 2, that's P. And Q is 5, 10. 1, 2, 3, 4, 1, 2, 3, 4, 5, and that's the 10 there. There's Q. Vector PQ. I'm just going to put it in a different colour so it's easier for me to see where it is. So there's PQ. Goes from P to Q, and we want something that makes an angle of 30 degrees. So 30 degrees is about a third of a right angle, so there's a right angle there. And a third of that would be sort of this way. And there's probably one going to be on this side too. Okay. And if we want them to be unit vectors, then they should... If we want them to be unit vectors, then they should be length 1 as well. So this length is 1, so about that long. So I'm expecting there to be 2 of them. Okay, 1 on each side, because they're both 30 degrees one way or 30 degrees the other. So from the diagram, we expect 2 vectors. But hopefully the maths bears that out. Okay, so I have a feeling it's going to be easier to talk about this if I give a name to the vectors I'm looking for. But before that, I think it might be useful to find the coordinates of the vector PQ. So PQ is end minus beginning, Q minus P. 5, 10, minus 2, 3. 5 minus 2 is 3. 10 minus 3 is 7. That makes sense. 3 across 7 up. Fabulous. Okay. And let W be a unit. Oh, let's call it U for unit vector. Vector at 30 degrees from PQ. Okay, so being a unit vector, it's length 1. And being at 30 degrees from PQ, I can do the angle. So I'm going to do the angle first, if that's okay. And it's going to be easier if U has coordinates. So let's let U be equal to I'm going to call it AB, if that's okay. You know what? I'm going to call it U1 and U2. Just to remind me that it comes from the vector U. Okay. So I know that the angle cos of 30 degrees is going to be equal to U dot PQ over the length of U times the length of PQ. Okay. Right. Well, let's see. Let's find each part of this. Now, cos of 30 degrees, I know what that is. I think it's root 3 on 2. Just a second. Yep. Just let me just draw 30 degrees is like a little angle, and normally I do half of an equilateral triangle. Yep, that'll work. Cool. Cos of 30 degrees is root 3 on 2. U dot PQ is U1 U2 dot 37, which is 3U1 plus 7U2. Okay. The length of U is 1 since it's a unit vector. And the length of PQ is the square root of 3 squared plus 7 squared, 9 plus 49, which is the length of 58. Okay? The square root of 58. Actually, 58 is a multiple of 4, isn't it? No, it's not. Because 50 isn't and 8 is, so that's not going to work. Okay. Cool. And so we can sub all that into our equation, right? So therefore, root 3 on 2 is 3u1 plus 7u2, that's the dot product, over 1 times root 58. Okay, so root 3 on 2 times root 58 is 3u1 plus 7u2. Well, that's sort of the best I've got. I haven't really got anything else useful to do with that. Okay. What other information have I got? Well, I've already used the fact that the length of u is 1, but I guess I could use it again to make an equation involving u, right? Okay. Also, the length of u is the square root of u1 squared plus u2 squared. And that's 1 since it's a unit vector. So u1 squared plus u2 squared must be 1 squared, which is 1. There's all these squares here. I guess if I squared this one, then I would get squares. Or if I rearrange this one to get u1 in terms of u2, yeah, that might work. Okay, so now let's give this a number and this a number. So from number 2, I've got that root yeah 174 over 2 is 3u1 plus 7u2. So root 174 on 2 minus 3u1 is 7u2. Okay, oops, sorry, off the page, off the screen. Just going to write it like this. If we do a seventh of that, that's what u2 is. Okay. So what if I sub this back into 1, and I'll get u1 squared plus 1/7 times a half of root 174 minus 3u1 squared is 1. And that's totally a quadratic equation in u, 1. So it should technically be possible to figure out an answer for that, which would have to happen via the quadratic formula. I can't think of any other way. I'm going to have to expand that out. Oh, it's not going to be fun, people. Rightio. So I get 1 on 49, and I've got a half of root 174 minus 3u1 squared. It's 1. Well, I guess I get this squared, which is a quarter of 174, like a half squared is a quarter and root 174 squared is 174. And I'll have this squared, which is 9u1 squared. And I'll have 2 times this, which would be minus 3 root 174 u1. And that's going to be equal to 1. Ugh. What if I just multiply everything by 49? Well, 174 on 4. And 74 divided by 2 is 87. 1, 49. And so I've got that this minus that would be 40. And that's a quadratic equation, and so therefore I can figure that out. It's nearly there. It's 49 times 2, 98 on 2. Okay. I think I might just times everything by 2 just to make it complete. Okay, and so u1 will be minus b plus or minus b squared minus 4 times a times c over 2a, which will be whatever it is. 6 times 174. Which is an unhelpfully negative number. I feel like I probably did something wrong along the way somewhere. Because there really should be 2 answers, shouldn't there? Definitely root 58. $174. My dot product is right, is it? Yes. Subtract 3u1 divided by 7. I square it. 149. Whoa. I know this is this squared. And it's 2 times this, so the 2 times a half would cancel each other out. And multiply by 49. 40 there. Didn't do anything to this. Seven. $49. It's minus 185. Which would make that a plus. Okay, 36 times 174 plus 4 times 80 times 185. The square root of that answer. So it's whatever it is. There's all these answers There's two of them. So minus 6, no, we're going to go in brackets. Minus 6 times square root of 174 minus the square root of 36 times 174 plus 4 times 80 times 185 divided by 160. So minus 2.094 approximately. And we go back and we put a plus in this spot instead. Approximately. Which means the U2 we could get from either of these equations. We actually have a formula for U2 here, and so therefore U2 is I just lost my answers. All right, times that minus 3 plus a half times root 174 and divided by 7. Which is 0.469, or that's this one. So minus 6 times root 174 plus minus the square root of 36 times 174 plus 4 times 80 times 185 divided by 160. And then times by minus 3, and then plus a half times root 174, and then divided by 7. It distresses me that that's not going to be a unit vector. Right. I made it really complicated for myself, and I'm really sorry to be giving you a problem that isn't working out nicely. Okay, so something is wrong somewhere, and I can't quite figure out what it is at the moment. Now I've got a different answer again. That's because I didn't put brackets in. Oh, okay. Let's try that again. Minus 6 times 174 bracket go right back to the beginning. Should be another bracket there. Right, that's a much nicer answer. I should have noticed it when my answers came out to be greater than 1. just going to store this in A, right, so that I can reuse it later. It's reminding itself in the calculator where that is. I wish this calculator went back more than one step. Okay. Minus 6 times root 174 plus the square root of 36 times 174 minus 4 times 80 times minus 185 divided by 160. Still shouldn't come out as more than 1, should it? Because if they square to add up to 1, then they could both have to be less than 1. Okay. Minus 6 times root 174 plus that answer. Right. 0.982. Let's just store that in B. Recall A. Right. One seventh times 1/2 times root 174 minus 3 times A. 0.186. Minus 0.151152. All right. Let's just check if things are working correctly now. 0.195 squared plus 0.186 squared. I'm about ready to give up, you know. This one's working about right. This one not so much. Let's just go back to here. Square root of 36 times 174 minus 4 times 80 times minus 185 is that. So minus 6 times root 174 minus that answer divided by 160. For the sake of Frel. Square at the answer. 6 times. I'm just... I just paused the video for a minute while I went and got really frustrated, and I've discovered a problem. And my problem is that way back here when I had a plus, it somehow became a minus on the next line. So that's actually supposed to be a plus, which which means this is supposed to be a plus, which means this is supposed to be a plus. And so that's not 49, but 58. And that's not minus 87, but a plus. And that's not plus 3, it's a minus 3. And so everything on this page is just wrong. And so I actually have 58 u1 squared plus, well, let's just multiply everything by 2 from this stage, just to get rid of this 2 here. So 58 times 2 is 174, and that's 87 minus 6 root 174 u1 is 98. And 87 minus 98 would be minus 11. And now we can do our quadratic formula. Minus b plus or minus b squared minus 4 times a times c over 2a. And that's 6 root 174 plus or minus, and both of these have a 174 in them, so I'll pull that out. And then what I have left is a 36 plus a 44, which is 80. But I'm just going to put that in explicitly. Which is 6 root 174 plus or minus root 174 times root 80. If I divide everything by root 174, I get this, which is a particularly pretty answer, I must say. And the 80's got a multiple of 4, so I can pull that out. It's actually a multiple of 16. So that's 6 plus or minus 4 root 5 over 2 root 174, which is lovely. 3 plus or minus 2 root 5 over root 174, which is really not too bad, actually, compared to everything else, all the awfulness I had before. And so, therefore, my u2 would be, well, whatever I get when I sub that back into the other formula. And so just for completeness' sake, that's approximately equal to 3 minus 2 square root 5 divided by root 174, which is minus 0.112. And we can go back and do the same thing with a plus. Whoop. 3 plus 2 root 5. Divided by, 0.566, and then u2, which is 1/7 of 1/2 of 1 root 174 minus 3 u1, which I can't be bothered doing exactly. It's going to be a weird-ass thing. I don't like it. So that's going to be approximately equal to, well, that's my 0.566, so let's times that by minus 3 and add 1/2 of 174 and divide that by 7, 0.699, and then with the other one, 3 minus 2 root 5. And we take that answer times minus 3 plus a half times root 174. And let's just check. Minus 0.112, well, I don't really need the minus, 0.112 squared plus 0.990 squared. It's looking pretty good. It's about 0.99, and 0.566 squared plus 0.699 squared. I feel like I've done something wrong there, because that's not adding up to anything close to 1. So 3 plus 2 root 5 divided by root 174, 566, yep, times minus 3 plus a half times root 174 divided by 7, 699 squared. Oh, I really thought I had it. I really did. It was so close. Here over on my computer I put in my original equation and asked it to solve it for me. This one back here. This one back here. Oh, sorry. This one back here. And so I can use and it says that the zeros are minus 0.118 and 0.801 according to the graph. There and there. So and the U2 should be this thing. Which is that, 0.993. 0.599. So when I just check that this is working the way it should, 0.118 squared, whoop, 0.993 squared is about 1, 0.801 squared plus 0.599 squared is about 1. Oh, and so it's working. Wow. I'm very sorry that that turned to crap. I really should have found one that wasn't quite so crappy. At 30 degrees from, what was the name of the vector? PQ. Approximately minus 0.198, 0.993, and 0.801, 0.599, which according to my diagram, yeah, one of them should be going backwards and up and the other one should be going forwards and up, so it's not too bad. Oh, all right. Well, I was going to do another example, so if you've borne with me this long, then you should be rewarded. So find all unit vectors perpendicular to v, which is going to be 3, 8. Okay, this one's going to be quicker. All right, so what I'm going to do is I'm going to let u be a unit vector perpendicular to 3, 8. And I'm going to write u being u1 and u2. So to be perpendicular to 3, 8, its dot product with 3, 8 must be 0. Since u and 3, 8 are perpendicular, u dot 3, 8 must be 0, which means u1 dot u1 u2 dot 3, 8 must be 0, which means 3u1 plus 8u2 must be 0. Okay, so I can actually write u1 in terms of u2, or u2 in terms of u1. So 3u1 is minus 8u2, and so u1 is minus 8/3 of u2. I could just as easily have written u2 in terms of u1, but that's good, and that's a nice simple relationship between u1 and u2. Okay, right. So now I need a unit vector, right? But I can find just a vector that's perpendicular to 3, 8. For example, if u2 is equal to 1, then u1 would be minus 8/3 times 1, which is minus 8/3. And the vector 1 minus 8/3 is perpendicular to 3, 8. Now, any multiple of this vector will also be perpendicular to 3, 8. And so I might actually say that. So out of all of those possible multiples, we want to choose the one that has length 1. Which means what we should really do is just divide this one by its length. But it might be easier to choose a different vector. And I should really just give it a name. Okay, in particular, w is like minus 8/3. It's perpendicular to 3, 8 because it's a multiple of this vector. And we can find a unit vector by dividing this one, by multiplying this by 1 over its length. So the length of w is the square root of minus 8 squared plus 3 squared, which is the square root of 64 plus 9, which is the square root of 73, which is not a square number and nothing nice goes into it, so I'll have to leave it with that. And so 1 on root 73w is a unit vector. So therefore, a unit vector perpendicular to 3, 8 is 3 on root 73, 8. No, sorry. is minus 8 on root 73, 3 on root 73, because that's what 1 on root 73 of W is. Okay, so that's one of them. If I think about a diagram of what's going on here, I don't really know where V is starting, so I'm just going to put it at the origin. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's the vector V. And then minus 8, 3 is over this way. 1, 2, 3, 4, 5, 6, 7, 8. That's the vector W that I found. Yeah, and it's at right angles. And the unit vector is there. So there should be another one over this way that's also at right angles here. Okay, so it'll be minus this vector, because it's the same vector but pointing the other way. All right. So there's going to be exactly 2. So that means that the answer, if I had just asked find a unit vector perpendicular to 3, 8, then I could have stopped here and said, well, there we have one. If I just asked find a vector perpendicular to 3, 8, I would have stopped there at the minus 8, 3, minus 8 thirds 1. Okay? But if I just wanted a unit vector, it would be this one. And then that answer is not unique because there's more than one answer. When a mathematician says unique, they mean there's more than one answer. So that's what we mean by unique, and that's how you would find all of them. We used a geometrical property to prove that we had all the answers, because we know how perpendicularity works. But we could have done a similar thing to the previous one, where we went, well, we know that we could have done this, and this probably would have been actually slightly quicker. We know that U1 is minus 8 thirds of U2. And also, the length of U is 1, which means that the square root of U1 squared plus U2 squared is 1, which means U1 squared plus U2 squared is 1, which means that minus 8 thirds of U2 squared plus U2 squared is 1, which means that, sorry, there's not a bracket there, which means that 64 ninths of U2 squared plus U2 squared is 1. Which means that 73 ninths of U2 squared is 1, which means that U2 squared is 9 on 73, which means that U2 is 3 on root 73, plus or minus, which means that U1 is minus 8 thirds times plus or minus 3 on root 73, which would be minus or plus 8 on root 73. And so all unit vectors perpendicular to PQ, was it PQ? No, V, are 3 on root 73 minus, no, that's U2. The U1 is minus 8 on root 73, and that goes with a plus 3. And minus plus 8 on root 73, and that goes with a minus 3. So we could have done it that way if we wanted. Thanks for watching. Thanks for bearing with me while I gave up on my exact answers and used Desmos in the end to calculate it. But luckily you've seen that the errors are almost always one of copying down a minus wrong. Thanks for watching.